A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today, including my group here, this are going to introduce to you about single phase induction motor. So what is a single phase induction motor? And what does it differs than triple phase induction motor? So a single phase induction motor is a motor an AC motor that converts electrical energy into mechanical energy like this. You can take a look at the picture above me like this. Okay, so it operates only by using one power phase instead of three power, like that. And then since it just requires one power phase, it is much simpler, easier to repair compared to a triple phase induction motor. Why? Because it's just one. You just need you just need to repair just one thing, a single phase induction motor. Whereas in the triple phase, you have some weird three things, and then it's hard, And then the last one, because it is so much simpler, easier, and cheaper to use, right? So it is commonly used in residential houses and small offices.
A single-phase induction motor has a lot of components, but in this case, what we are going to focus to is the two basic parts of the motor, which are the stator and the rotor. In the same time, we will also learn about the winding mechanism, which will explain how the rotation happens. Firstly, let me introduce to you the stator. As its name indicates, stator is a stationary part of an induction motor. The stator is a hollow cylindrical core with the inner surface of the stator is made up of a number of deep slots, or also called grooves. It is into these slots that the windings are positioned. The arrangement of the winding within the stator determines the number of poles that the motor has. A standard single-phase motor typically has two windings, which are the auxiliary winding and the main winding. The windings will be explained more later on. Fun fact about the stator is not a one-piece hollowed cylinder. It is made up of a stack of round pre-punched laminations pressed into a frame. The laminations may be made up aluminum or cast iron. These stacked laminations will help to reduce eddy current losses. Still remember about eddy current?
Hi, I'm Nasrin. For the next part, we're gonna discuss about the construction of rotor. Rotor is a rotative part of an electric motor. The main components of rotor are rotor core, outer frame, and winding. The rotor is also built with a thin layer of lamination of the same material of the stator. The limited cylindrical core is mounted directly on the shaft. The laminations are slotted on the outer side to receive the conductor. A circular cage rotor consists of limited cylindrical core. The circular slot at the outer periphery are assembled grooves. Each slot contains an insulated bar, conductive aluminum or copper. At the end of the rotor conductor are short circuited by heavy ring of copper or aluminum. Okay, that's all from me.
Okay, what is winding? Winding is a wire part that can be found in the stator, which can be found on the groove of the stator in this induction motor. There are two types of winding in the stator, which those are main winding and also starting winding. They can be called auxiliary winding. Okay, for these two winding, the auxiliary winding is perpendicular to the main winding. Okay, to differentiate between these two winding, by look the number of the turn. If the winding has more turn, it will be the main winding, and while another one automatic will be the starting winding. Okay. For the function, starter winding. Starter winding, when the starter winding is energized by the single phase supply, the magnetic field or flux will be produced. At the same time, it will produce induced current in the rotor that can be related of Faraday's law of electromagnetic induction. So this induced current in the rotor will also produce alternating flux and make the motor move.
So I will continue the discussion of single-phase induction motor by talking about the operating principle, which is the double revolving field theory. The double revolving field theory stated that a pulsating magnetic field is resolved into two rotating magnetic fields, meaning that the sum of two oppositely rotating quantities equal to one fluctuating quantity. So, the pulsating magnetic field is divided into forward and reverse rotating field with the same magnitude. As stated just now, the net torque in the motor is equal to the sum of the torque due to each of the two magnetic fields. The equation for an alternating magnetic field is given as the alternating magnetic field equal to the maximum value of the sinusoidally distributed air gap flux density produced by a properly distributed stator winding carrying an alternating current of the frequency omega, and alpha is the space displacement angle measured from the axis of the stator winding. As we know, sin A cosine B is equal to the summation of half sin A minus B and half sin A plus B. So, we can write the equation 1 as follows to form the equation 2. The first term of right hand side of the equation 2 represents the revolving field moving in the positive alpha direction, which is forward rotating field. Similarly, the second term shows the revolving field moving in the negative alpha direction, which is backward rotating field. Thus, the pulsating magnetic field is resolved into two rotating magnetic fields. Both are equal in magnitude and opposite in direction but at the same frequency. At the standstill condition, the induced voltages are equal and opposite as a result. The two torques are also equal and opposite. Thus, the net torque is zero, and therefore a single phase induction motor has no starting torque.
Okay, I will continue why the single phase induction motor is not self-starting. So, assume this is the stator. Inside here is the rotor. Rotor won't start by itself. Okay, why? Because this is the main winding. We know it is supplied by a AC current, so the AC current will fluctuate this and this direction. So during this positive cycle, the magnetic field will be produced like this, and later for the negative side, the magnetic field will flip like this. So we know that the magnetic field is just fluctuating like this but not rotating. This won't produce enough torque to start the rotor. Okay, so to make the rotor inside this to start rotate, we need to add another winding, which is the auxiliary winding or the secondary winding. We supply also an AC current but 90-degree phase different to the main winding. So this is the first AC current, the main winding, and this is the second. So it will have like this two phase. Okay, from this we can create an rotating magnetic field. So from the first winding, it produces magnetic field like this, and the secondary winding, the auxiliary winding, produces magnetic field like this. So we can see that the magnetic field produced is the resultant by these two main winding. Okay, so we take a look at the moment for this number 1. at the number 1, currently there is no current at the second winding, only the first winding, so it will only have this magnetic field only for the number 1. On the second, both have magnetic field but positive direction, positive phase, so this the main winding will produce magnetic field like this, and the secondary winding will produce another magnetic field like this. So this is the same as this, the resulting magnetic field. So this is for only number 2. For number 3, there is no current for the first winding. For the main winding, there's only current for the secondary winding or the auxiliary winding. So this is the auxiliary winding, the magnetic field is only this. Okay, so if we continue through all this space using the same concept, we get that the magnetic field inside this is actually rotating. This is for the number 1, and the resulting magnetic field for the second is like this. And then the number 3 like this, and number 4, 5, 6, 7 and 8. So you can see that the magnetic field inside is just rotating like this due to the secondary winding. So using the secondary or auxiliary winding, we can get a rotating magnetic field inside this stator, which will rotate the rotor. But we won't need this secondary winding to run all the time, so later we will need to cut off this or disconnect this from the circuit. Okay, this is the circuit for the single phase induction motor. Okay, this is the main winding, and this is the second winding. Okay, the second winding we connected with a capacitor to make sure it is 90 degrees out of phase with the main winding, the current. Okay, we use a switch here to disconnect later. So because this is a single phase, not a second two phase, that's why it is called a single phase, but using two phase only for starting. The switch will disconnect it after the squirrel cage rotor will spin, reaching a 90 to 80% speed.
So for my part, I'm going to present the types of single phase motor. Okay, there are 5 types of single phase motor. The first one is the split phase motor, it is also known as a resistance start motor. As you can see here, this is the circuit diagram, where you can see there's auxiliary winding down here, and there's a main winding right over here, I guess. Can you please edit if it's not? Okay, and this split phase motor, this split phase motor is more suitable for easily started load where the frequency of starting is limited. The main winding of the induction motor was very low resistance and high inductive reactance. The example of where you can find this motor is in washing machines or in a food mixer. Okay, the next type of phase motor is a capacitor start motor. The capacitor start motor develops a much higher starting torque, and the value of starting capacitor must be large, and the resistance of starting winding must be low. Example that you can find this motor is in the conveyor or in a grinder. So this is the circuit diagram. As you can see, it is different from the split phase motor because there's a capacitor right over here. There's a capacitor here. Yeah. So that's the difference. And then the third type is the capacitor start and capacitor-run motor. It has a two-value capacitor motors. These two-value capacitor motors are used for loads of higher inertia that requires frequent start. As you can see in the circuit diagram here, there's a two capacitor, okay, in a parallel circuit. Example that you can see, this motor is in a refrigerator or in an air compressor. Okay, the fourth one is the permanent split capacitor. Okay, as you can see in the diagram here, there is no switch, okay, because the capacitor is permanently connected in the circuit at starting and running conditions. And of course, there is no centrifugal switch, and it has a higher efficiency, sorry about that, it has a higher efficiency, higher power factor, and a higher pull-out torque. This motor is used to operate office machinery and drive refrigerator compressor. Okay, the last type is the shaded pole motor. Of course, this is a most common used motor. These motors are very suitable for small devices because of their low initial cost and easy starting. It requires a low starting torque, and of course it is common found, and the example of this motor is on a table fan, exhaust fan, and hair dryers.